Welcome back. So let's talk about some hazards specific to coastal processes. Landslides are common in some coastal areas, earthquakes, depending on if we're looking at an active or passive margin, tsunamis, etc. But what we're going to talk about is kind of specific to coastal processes, the interacting of land and sea in only that specific instance. So again, who is impacted by these hazards? Individuals, obviously. This can come from, you don't even have to live there, but just visiting, swimming in the oceans, close to coastal areas can have strong currents that could affect, or could be a hazard. There's hazard to, obviously, property, safety, life during storm surges, tsunamis, landslides, earthquakes, what have you as well. But so these hazards affect individuals, they affect communities. You can get long-term hazards related to coastal erosion and rising sea levels, beachfront houses, businesses, lighthouse docks, roads, whatever, utility lines, pipelines, sewer systems, all at risk due to coastal erosion. So there's a number of different entities that can be affected by coastal hazards. And again, remember, 53% of the U.S. population lives in a county that touches a coast. That's a lot of people. So, rip currents. So rip currents are kind of interesting. So they're caused by this interaction between the ocean and the land. They're powerful currents that carry large amounts of water away from the shore. Sometimes they're known as riptide or undertow. If you've ever been to a beach, or you might have heard about this in movies, or surfing in California. So this is a very real hazard, and it has to again deal with how water interacts with the land, the coast. I'll show you. So rip currents are responsible for killing 200 people every year in the U.S., and about 20,000 each year in the U.S. need to be rescued from these types of currents. They kill more people on average than hurricanes or earthquakes combined each year in the U.S. So, there's these things that we think of that are deadly, hurricanes and earthquakes, yes, but sometimes it's the little things, the things we don't think about. So a rip current is, again, water moving away from the beach, and it can move away at speeds that can exceed 4 miles per hour, which, that doesn't sound like a lot. How fast can you swim? I bet it's not 4 miles an hour. I bet it's 2, maybe 1. So if you are getting pulled away from the beach in one of these rip currents at 4 miles an hour, and you're trying to swim back, it ain't going to happen. It ain't going to happen one bit. You can't swim that fast. Most normal humans can't swim that fast. So if you're trying to fight this rip current, imagine you're at the beach and I'm getting pulled out at this rip current. I'm going to get exhausted. I'm going to lose my energy to swim, and guess what? I'm going to drown. So here's the key, though. These rip currents, this kind of movement of water away from the beach, are relatively narrow. They're only from 3 to about 30 meters wide. So while it can pull you very fast away from the shore, they're actually not very wide. So in that case, instead of trying to swim back to the shore, you swim sideways. You swim parallel to the shore, not towards it. Then you swim back, and obviously do not panic. So if you swim off to the side, get out of this rip current, then you can go back forward. You're outside of this rip current. So how does this work? So you get the waves coming in, and due to just below the ocean surface, just due to natural factors, you can get this little area of little channel in the sand just below the ocean surface, and it only has to be a few feet. But the water wants to find the lowest spot, so it's going to all the water is going to find that lower location and kind of move out in this area. So if you're swimming in this area, you're going to get caught in this rip current and get pulled out, and you can get pulled out hundreds, thousands of feet, sometimes too far to swim back. So again, instead of trying to fight it, you just swim off to the sides and then swim back because then it's area as normal. So here's an area of rip current. So you can see kind of all the waves making its way in, but all that water for some reason funnels out this area. The topography just below the waves is just funneling all that water this way. So you get caught in this, you're just going to get sucked right out. and get sucked right out. So what you want to look for, and here's a bunch of surfers over here, here's a bunch of surfers over here, but no surfers right here. So you can see this area without any waves. That's because the water is kind of rushing back out that way, preventing the formation of waves. You get waves here, you get waves over here, but not here. As you can see, all the surfers are outside of this. That's the rip current. You can see how far you can get pulled out. And you get pulled out here, that's a long way to swim back. So, but you can see it's only, this wide. So if you're trying to get pulled out, you swim to the side. That's kind of what this illustrates. If you feel yourself getting pulled out, kind of swim off to the side, then come back in. All right. Stay calm, float, raise an arm to attract attention, swim parallel to the beach, conserve your energy. Waves can assist you back to the beach once you get back out of the rip current. So anyway, that's a kind of small hazard most people don't think about, but again, kills more people than earthquakes and hurricanes in the U.S. per year. And that's due to the water interacting with the shape of the terrain just below the surface. So not only that immediate threat, but over time you can get coastal erosion. The breaking down of material, the taking away and transport of material, so things are falling now into the ocean. So beach erosion can be caused by some short-term things. Seasonally, if you go, for instance, if you go to the beach in San Diego in the winter or summer, the amount of beach might look a little bit different. It has to deal with different weather patterns, causing more sediment to wash up on the beach or get pulled out away from the beach, but that can be seasonal. That can be a normal fluctuation. So those are short-term causes. Storm-related, a big storm rolls in, it might take away some sand and sediment, but that material might be deposited in the next week or two. So beach erosion can be short-term, but it can also be long-term. Climate change can be driving that. How we impact the coast can also drive how the coasts erode. For instance, a lot of times beaches require some sort of bank of sediment, some deposition of sediment somewhere to maintain the beach. Typically, that's coming from streams on land, carrying with it sand, silt, sediment, and kind of as they wash into the ocean, that gets deposited right in the area where that stream hits the ocean, nourishing the beach naturally. But if we start to dam up rivers, we're also damming up the sediment supply, the sediment delivery mechanism from rivers to beaches, from land to ocean. So as far as a long-term cause, looking at climate change or short-term causes, Miami Beach we'll talk about in lab a little bit more. But Miami Beach, in this case, before and after Hurricane Irma. So this was kind of be more of a short-term thing. But Miami Beach overall, due to climate change and sea level rise, well, you'll see. Miami Beach will be gone in a few decades. Please don't go to Miami Beach. If you've never been to Florida, it's horrible. It's hot to begin with. But it's going to be underwater. You'll see in lab. But in any case, so here's an example of a short-term beach erosion due to a hurricane. So you can see how much of that beach has been eroded away due to a storm. That's just one storm. Here's another hurricane, Hurricane Sandy, kind of really affected areas up to the north. We talked a little bit about this in lecture last week. But you can see this is Wallops Island, Virginia, so right on the coast. You can see the beach before August 2012, and then after, looking at this structure here, how much beach is here versus how much is gone. Hurricane Sandy really causing that short-term erosion. So not only can we talk about beach erosion, but we can also have cliff erosion, and this is mostly due to the wave action. So as the waves kind of hit these cliffs, it really eats out the bottom of the cliff. And if you're starting to eat the bottom of the cliff and there's nothing to support the top part of the cliff, well, that top part of the cliff is going to fall in, and the cliff kind of just makes its way backwards. So this is responsible for land erosion, landslides as well. It could also be caused by human activities, uncontrolled surface runoff, so putting more water into the ground, making it more saturated, increasing groundwater discharge, additional weight on tops of cliffs, building buildings and houses and structures. All of that can put pressure or loosen up the material, and as waves more easily eat it, the cliff is more easily eroded. Before we move on, let me give you part of the super secret code. It is the number 3. You got me? The number 3. One more time, the number 3. So here is a cliff. This is actually on the Great Lakes, so it doesn't have to be on the oceans at all. So here's the Great Lakes. You can see these beautiful houses. In fact, it looks like they're just building this one up here. Looks like, because I can see some construction stuff up here. But look at this cliff. Look what it's made out of. Does that look like hard, sturdy rock to you? That's just like loose sand all this stuff is built on. Do you think this stuff is, resists wave action, or it's pretty easily eroded, eaten away? Guess what? It's pretty easily eaten away. It's pretty easily eroded. This stuff can just get eaten up. So you get a number of storms eating at the bottoms of these cliffs, and the top part of the cliffs falls in and just kind of makes its way back and back and back. I wouldn't build a new house right there if I was them. But obviously it happens on coasts as well. This is more indicative of active margin kind of cliffs, not a lot of beach. But again, you can see the cliff erosion here. So the cliff itself is back here. This is just the pile of dirt and sediment that has eroded away. So we don't necessarily measure to this, but we would measure how far the ocean goes back to this cliff face here. You can see, here's another, I believe this is California. You can see how parts of these backyards are just falling down, falling into the ocean. Here's another one. People still live here. Look at that. Your backyard is now in the ocean. People are still living here. Again, California. And here's a really kind of a newer example. In California, you're adding a bunch of pressure right on these cliffs with these apartments. So these looks like these apartments may be built in like the 60s or 70s or something like that, kind of looking around here. I'm sure they were a gorgeous place to live, but you're, again, applying pressure on top of this cliff, causing it, as the waves kind of eat the bottom of it, it's really pushing down that material, causing it to erode faster because you're applying pressure on top. As the bottom of the cliff is being eaten away, that thing on top is really pushing down on it, making that stuff slide down more and more and more. So these were condemned. These were actually ripped down. We'll touch on this in lab. Here's a little thing you can watch. You don't have to necessarily watch it, but it does paint the picture. It can be helpful in lab. So it's just a quick little news article on this area of California. But you can see they tried some things here to kind of stabilize the slope by putting some, looks like concrete and big bolts in the cliff face here to try and keep it intact, but it didn't seem to work very well. Yeah. Again, looking at this cliff, does this look like solid rock to you? No. All this rock, they put that there to kind of take the energy from the waves and hopefully dissipate it a little bit. So that's one strategy that you can use to help dissipate the energy of waves. So those aren't natural. Those were placed there to try and save the cliff, but it really didn't help. So this was in Pacifica, California. The cliff has retreated episodically at an average rate of 1.5 to 2 feet per year over the past 146 years. We know this. People still built and live there. Wave-induced undercutting caused this cliff to naturally just get eaten back. Reduction in beach width over time. So the beach is getting eroded away. A reduction in cliff face stability owing to the infiltration from heavy rains. So more water going into this relatively soft cliff. Erosion of the cliff face by groundwater piping. So putting pipes in there, disturbing the integrity of the cliff itself. Increased weight from that residential structure on top. All of that. And this is what you get. This is what you get. So anyway, more on this area in lab, Pacifica, California, but it's a decent recent example of, where the ocean meets the land, the ocean's going to win. And where humans are at, the ocean's going to win. It's going to happen. So we'll pause here. I think when we'll come back, we'll knock off a couple more sections. So I'll see you back here in just a second.